So I want to start with a sentence that actually appears at the end of a real, published Google research paper. After running a huge number of experiments and improving one of the core pieces of the transformer, the author basically shrugs and says he cannot explain why it works, and jokingly credits the improvement to something like divine benevolence.
Wait, hold on. A serious machine learning paper just gives up and blames a higher power. That is either the most honest sentence in AI research or the most suspicious one, and I need to know which.
Honestly, it is a bit of both, and that is exactly why this paper is worth talking about. It is called GLU Variants Improve Transformer, written by Noam Shazeer, and it quietly became one of the most influential four-page papers in modern AI.
4 pages? That is barely longer than the introduction of most papers we cover. What could possibly fit in 4 pages that ends up mattering this much?
That is the fun part. It is a tightly focused experiment on one specific piece of the transformer that most people never think about. Everyone talks about attention, the part of the transformer that lets it relate different words to each other. But there is a second, quieter piece doing a huge amount of the work.
Okay, before we go further, why should I care about some obscure internal piece of a neural network? Most listeners are not going to know what that even is.
Fair question, and here is why it matters. This obscure piece, called the feed-forward layer, actually makes up a massive share of the total parameters and computation in a transformer. So, if you find a way to make it even slightly better, that improvement gets multiplied across every single layer of every single model built on this architecture. So let me actually explain what this feed-forward layer does. After the attention step lets each word look around and gather context from other words, the feed-forward layer takes that result and processes it individually, transforming the representation before passing it to the next layer.
Give me a picture I can actually hold on to here, because processes the representation is very vague.
Think of the transformer as a factory floor. Attention is the meeting room where every worker compares notes with every other worker, and the feed-forward layer is the private workstation where each worker takes what they learned and refines it on their own before the next meeting. For years, that private workstation used a very standard tool called RayLU, or later something called GELU, which are just mathematical functions that decide how much of a signal gets passed through. Nobody was really questioning whether that tool was the best possible choice. It was just the default.
So this paper is basically someone finally asking, wait, why are we all using the same default tool without testing the alternatives? That is a very simple question to build a whole paper around.
Exactly, and that simplicity is part of what makes it so interesting. Instead of inventing some brand new complicated architecture, the author borrowed an idea from an older type of neural network called a gated linear unit, or GLU, and asked what happens if we drop that into the transformer instead. Now here is why the gating idea matters in the first place. A single activation function like RayLU only gets one shot to decide, in one pass, how much of the incoming signal to keep or throw away. A gated unit works differently. It creates two separate projections of the input and multiplies them together, where one of those projections acts like a gate controlling how much of the other one gets through. So instead of one pathway making a decision, you get two pathways interacting with each other. Here is an analogy that might help. Imagine two people carrying a message. One person is the messenger holding the actual content, and the other person is a gatekeeper standing at a door, deciding how loudly or quietly the message gets allowed through. Multiplying those two together gives you a much more flexible signal than just having one person shout the message at a fixed volume. So bringing that back to the paper, the author tests several flavors of this idea inside the transformer's feed-forward layer. There is a version using a sigmoid gate, a version with no gate at all called bilinear, a version using a RayLU style gate, one using a GELU style gate called GEGLU, and one using something called SwiGLU.
That is a lot of acronyms for what sounds like the same basic trick with different flavors sprinkled on top. Does swapping out the flavor of gate really make a measurable difference? Or is this just naming variations for the sake of a paper?
That is the right skepticism to bring, and it leads straight into the tricky part of the design. Because these gated versions need three separate weight matrices instead of the usual two, they technically add extra parameters and computation. To keep things fair, the author shrank the hidden size of these new layers by 2/3, so every single variant tested ends up using the same number of parameters and the same amount of computation as the original design. That way, any improvement you see is not just coming from the model secretly getting bigger.
Okay, that is a genuinely important control, because so much of deep learning improvement claims turn out to just be, we gave it more parameters. I will give them credit for closing that loophole.
Right? And once that control was in place, they built these different feed-forward variants into a full-size transformer based on the T5 model architecture, with 12 layers in both the encoder and decoder. Then they trained it the same way T5 was trained, predicting missing chunks of text pulled from a huge web text dataset called C4. After that pretraining stage, they took each fully trained model and fine-tuned it on a big collection of language understanding tests, including question answering with SCAD, and two well-known benchmark suites called GLU and SuperGLU, which test things like sentence similarity, logical entailment, and reading comprehension.
So now I want the actual results. Did the fancy gated version win, or did the boring old default hold its ground?
The gated versions won, fairly consistently. During pretraining, the two variants called GEGLU and SwiGLU produced the lowest, meaning best, perplexity scores, beating the standard RayLU and GELU-based layers at the exact same parameter and computation budget. Then on the downstream fine-tuning tests, the pattern held up. Across the GLU benchmark, the SuperGLU benchmark, and the SCAD question answering test, the new gated variants came out on top of the leaderboard in most cases, sometimes by a small margin and sometimes more noticeably.
Now here is where I want to slow down, because this is exactly the kind of result that sounds impressive until you look closely. I have some real pushback.
Go for it, that is what this segment is for.
First, these fine-tuning numbers came from a single fine-tuning run per model, not multiple runs averaged together. When you are talking about score differences that are sometimes less than 1 point on a 100-point scale, a single run is not exactly bulletproof evidence.
That is a completely fair point, and honestly the author says almost the same thing in the paper, calling the results noisy. The saving grace is that this effect does not show up in just one test. It shows up across pretraining perplexity and three separate and very different fine-tuning benchmarks, which makes it harder to dismiss as pure luck.
My second issue is that there is no single winner. Sometimes GEGLU is best, sometimes SwiGLU is best, sometimes RayGLU, or even the simple bilinear version wins a specific task. That inconsistency makes "we found the best activation function" a much weaker claim than the framing suggests.
Also fair, and I think the honest way to state the finding is narrower than that. It is less "we found the one true best gate," and more, almost any gated variant tends to beat the old ungated default, which is still a meaningful and useful discovery even without a single champion.
And my last point brings us back to where we started. The paper openly admits it has no theoretical explanation for why any of this works, and jokes about divine benevolence instead of giving a real mechanism. For me, that is a little uncomfortable, because it means we are optimizing by trial and error rather than understanding.
I think that discomfort is actually a really honest snapshot of where a lot of deep learning research sits, even today. Researchers often find that something works well before anyone fully understands why it works, and the theory tends to catch up years later, if it catches up at all.
Okay, so let us talk impact then. Because if this thing does not even have an explanation behind it, does it actually matter outside of this one paper?
It matters a lot, and here is the key reason. This improvement came at zero extra computational cost. In large-scale AI, compute is incredibly expensive, so a change that improves quality without requiring more memory or more processing time is about as valuable as an improvement can get. Because it was such a simple drop in replacement, this exact idea, particularly the SwiGLU variant, ended up getting adopted well beyond this one paper. Many of the large language models that came after this research, including some of the big, well-known systems people use today, quietly built this gated feed-forward design into their architecture.
That is honestly wild to think about. Something this small, tested in a 4-page paper with a joke about divine intervention at the end, is sitting inside massive AI systems that millions of people talk to every single day.
That is really the heart of the story here. Sometimes the biggest, most widely used ideas in AI are not some giant theoretical breakthrough. They are a small, carefully controlled experiment that just happens to quietly work better, and then gets copied everywhere because nobody has a reason not to use it.
And that is a wrap for this episode. If you found this conversation valuable, consider subscribing and turning on notifications. We release new research breakdowns regularly, helping you stay on top of the latest discoveries without having to read every paper yourself. Thanks for listening, and we will see you in the next one. Goodbye.